In this video, we're going to look at finding the probability of a union of two sets. So we have some definitions to start with. First, the intersection of events E and F, denoted by E intersect F. We've seen this notation earlier in the semester when we were working with sets, is all of the outcomes that are in both E and F. So the intersection of events E and F will be the outcomes that E and F both have in common. The union of events E and F, denoted by E union F, and again we saw this notation when we worked with sets way back earlier in the semester, is all of the outcomes that are in either E or F or both. So if an outcome is in E or F or both, then that outcome will be in the union of E and F. Now, looking at rules for computing the probabilities of a union of two events. If E and F are events, then the probability of E union F is equal to the probability of E plus the probability of F minus the probability of E intersect F. If E and F have no outcomes in common, they are called mutually exclusive events or disjoint events. So mutually exclusive events, disjoint events, those two terms mean the same thing. In this case, because E intersect F equals the empty set, the preceding formula simplifies to the probability of E union F equals the probability of E plus the probability of F. So what this last part's saying is, if E and F are mutually exclusive, in other words, if they don't have any outcomes in common, then the probability of E union F is simply equal to the probability of E plus the probability of F. However, if E and F have outcomes in common, if they're not mutually exclusive, then the probability of E union F is equal to the probability of E plus the probability of F minus the probability of E intersect F. So we have two different rules for computing the union of two events. One where the two events are not mutually exclusive and another where the two events are mutually exclusive. So take a look at example 4. Suppose the probability of E equals 0.51, the probability of F equals 0.38, and the probability of E intersect F equals 0.19. Find the probability of E union F. Well, this example is just directly using our first rule here. So the probability of E union F, the probability of E union F is equal to the probability of E plus the probability of F minus the probability of E intersect F. Well, we're told the probability of E is 0.51, so that's 0.51. We're told the probability of F is 0.38, so that's 0.38. And we're told the probability of E intersect F is 0.19, so minus 0.19. So if I want to know the probability of E union F, I just have to add and subtract here. So if I bring in my calculator, 0.51 plus 0.38 minus 0.19, that is equal to 0.7. So the probability of E union F would be 0.7. Look at 5. Suppose the probability of E is equal to 0.26, the probability of F is equal to 0.47, and the probability of E union F equals 0.62. Find the probability of E intersect F. Now in this problem, it's very similar to example 4, but in this problem we're given the probability of the union of E and F, and we're asked to find the probability of the intersection of E and F. So that's what makes this problem different. We can work it basically the same way though. The probability of E union F is equal to the probability of E plus the probability of F minus the probability of E intersect F, and so we fill in what we know. We know the probability of E union F is 0.62, so I have 0.62 is equal to the probability of E, which is 0.26, plus the probability of F, which is 0.47, and minus the probability of E intersect F, which is what we're looking for. So if I add up 0.26 and 0.47, that's going to add up to be 0.73. So I have 0.62 equals 0.73 minus the probability of E intersect F. So if I solve this like an equation, I can subtract 0.73 from both sides. So if I subtract 0.73 from both sides, then coming over here, 0.62 minus 0.73 is going to be negative 0.11, and that's going to equal minus or negative probability of E intersect F. So if I divide both sides by negative 1, then I get 0.11 or 0.11 equals the probability of E intersect F. So the probability of E intersect F has to equal 0.11. So again, we're just using our probability rule for the union of two events. Now let's apply that to a scenario. Take a look at example 6. Suppose one card is selected from a standard 52 card deck. What is the probability that A, the card is a diamond or a face card, B, the card is a 2 or a 3, C, the card is a 9 or a 10 or a heart, D, the card is red or an ace, and E, the card is not a face card. So we have several problems here that we want to answer. So the card is a diamond or a face card. Well, then that would be the probability that the card is a diamond plus the probability that the card is a face card minus the probability that it is a diamond intersect a face card. So now we have to think about this a little bit. First of all, it's a 52 card deck. In the 52 card deck, there are 13 diamonds. And just in case you're not familiar with a deck of cards, this would be a deck of cards. This is a standard 52 card deck. So we have 4 suits. We have clubs, spades, hearts, and diamonds. And we have 13 of each one of those. So 13 clubs, 13 spades, 13 hearts, 13 diamonds. And those have faces of ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. So each suit has those 13 different outcomes. So we're looking for the probability of diamond. Well, there are 13 out of 52 diamonds, so that would be 13 out of 52, plus the probability of a face card. Well, again, if I pull back in my picture to think about this, the face cards are the jack, queens, and kings. So we have 3 face cards in each suit, 4 suits, so there's a total of 12 face cards. So we're going to add 12 face cards. Now, minus the probability of being a diamond and a face card, so the intersection of diamonds and face cards. Well, if we look down here at the diamonds, there are 3 face cards that are diamonds. So we're going to subtract out 3 out of 52. Now, why do we have to do this? Why is this our rule? Well, let's take a look at this. Well, if we were to just add the 13 diamonds, we would be adding up these 13 cards. And if we were to add the face cards, that would be these 12 cards. The trouble is that the jack, queen, king of diamonds is both. So if we add up 13 and we add up 12, we would be counting these three cards twice, and that would be the wrong probability. So that's why we have to subtract off that intersection. We don't want to count the Jack, Queen, and King of Diamonds twice in our probability. So if we do this, 13 out of 52 plus 12 out of 52 minus 3 out of 52, well, we can just add the numerators. 13 plus 12 is 25, and 25 minus 3 is 22, so that would be 22 out of 52. The probability that the card is a diamond or a face card, or both, is 22 out of 52. Now we can simplify that. 22 and 52 can both be divided by 2. So 22 divided by 2 is 11. 52 divided by 2 is 26. So we could reduce that and say that is 11 out of 26 probability. If you want, we could also change that to a fraction. So that would be about a 0.423 probability. So this would be approximately a 0.423 probability. So about a 42.3% chance that the card would be a diamond or a face card. Take a look at B. What is the probability the card is a 2 or a 3? Well, this problem is a little bit different because a card cannot be a 2 and a 3 at the same time. In other words, the event being a 2 and the event being a 3 are mutually exclusive in this case. So in this case, all I really have to do is find the probability of being a 2 plus the probability of being a 3, because the probability of being a 2 and a 3 at the same time would be 0. Well, if we think about our deck of cards again, there are 4 2s and there are 4 3s. So the probability of the card being a 2 would be 4 out of 52, plus the probability of the card being a 3 would be 4 out of 52. And so if we add that, that would be 8 out of 52. Now 8 out of 52 can reduce, that fraction can reduce. 8 and 52 can both be divided by 4. 8 divided by 4 would be 2. 52 divided by 4 would be 13. So we have a 2/13 probability. And if we want to see what that is as a decimal, that would be approximately 0.154 if we round to 3 places. So about a 15.4% chance. Take a look at C. What is the probability the card is a 9 or a 10 or a heart? So we're looking at the probability of being a 9 or a 10 or a heart. So let me write that down a little bit differently. Well, in this case, first of all, recognize that being a 9 and being a 10 are mutually exclusive, just like 2 and 3 are mutually exclusive. So I could also think of this as the probability of 9 or 10 union heart. Now the card can be a 9 or a 10 and a heart at the same time. So I'm kind of thinking about it that way. So can I find the probability of being a 9 or a 10 plus the probability of being a heart and subtract out the probability of being a 9 or a 10 and a heart at the same time? Well, there are 4 9s and there are 4 10s. So there are 8 9 or 10s. Again, those are mutually exclusive. So the probability of being a 9 or a 10 would be 8 out of 52. Incidentally, just like the probability of being a 2 or a 3 was 8 out of 52. The probability of being a heart, well, that is 13 out of 52 because there are 13 hearts. Now the probability of being a 9 or a 10 and a heart, let's again look at our picture. 9 or a 10 and a heart, Well, there are 2 cards in that intersection because we have the 9 of hearts and the 10 of hearts that are both 9 or 10 and a heart. So I'm going to subtract off 2 out of 52 because that is the intersection of 9 or 10 and being a heart. So now I figured that out. I just have to add it up and subtract. So 8 plus 13 is 21, and 21 minus 2 is 19. So that probability would be 19 out of 52. 19 out of 52 does not reduce, so the probability that the card will be a 9 or a 10 or a heart is 19 out of 52. Again, if I want, I could write that as a decimal, so that would be approximately 0.365. So this would be 0.365 approximately. So if I randomly draw a card from a standard deck of cards, then there's about a 36.5% chance that that card will be a 9 or a 10 or a heart. D. What is the probability the card is red or an ace? So the probability of red or an ace. So that's going to equal the probability of being red plus the probability of being an ace minus the probability of being red and an ace. Well, how many red cards are there? Well, again, if we just take a look at our standard deck, half of the cards are red. So the probability of being red is half, or 26 out of 52. So 26 out of 52 plus, what's the probability of being an ace? Well, there are 4 aces. So the probability of being an ace is 4 out of 52 minus the probability of being red and an ace. How many red aces are there? Well, there's 2, the ace of hearts and the ace of diamonds. So the probability of being red and an ace is 2 out of 52. So now if I add this up, 26 out of 52 plus 4 out of 52, that's 30 out of 52, minus 2 out of 52, that is 28 out of 52. So the probability that the card is red or an ace is 28 out of 52. Again, that will reduce. 28 and 52 can both be divided by 4. 28 divided by 4 is 7. 52 divided by 4 is 13. So we have a 7/13 probability. Again, if I want that in decimal form, that would be about 0.538. So this probability would be 0.538 approximately. So about a 53.8% chance that the card will be red or an ace. Last but not least, our last question here for this example, what is the probability the card is not a face card? So this is back to the idea of the complement. So the probability of not being a face card is going to equal 1 minus the probability of being a face card. And we said there are 12 face cards, so this would be 1 minus 12 out of 52. Now 12 out of 52 will reduce, so that would be 1 minus 3/13. And I'm getting that because 12 and 52 can both be divided by 4. 12 divided by 4 is 3. 52 divided by 4 is 13. And 1 minus 3/13 would be 10/13. So the probability that the card's not a face card is 10/13. Or if I want that in decimal form, that would be about 0.769. So approximately 0.769 would be that probability. So we have one example left, but this video is getting a little long, so I'm going to look at that last example on the next video.